This is your first physics lecture from Chapter 2 entitled Picturing Motion. It corresponds to Section 2.1 in your textbook, and it's really the beginning of the physics coursework that we're going to perform over the course of the year. This is a very simple, very common sense concept that's given to you in this section, so the lecture is going to be fairly short. If there are concepts that I run over too quickly that you don't understand, make sure that you ask for a little extra explanation in class. In this lecture, we're going to talk about motion, what it is, how we're going to study it. We're also you're going to be introduced to two different types of ways to represent motion, called motion diagrams and particle models. And that's really it for the lecture. I'll give you your problem set at the end and also give you the particulars on a mini lab that I want you to complete in addition to your problem set. Now, in terms of studying motion, we have kind of a fancy word for motion in physics, and it doesn't include just motion, but all the things that happen when we're studying motion. And that fancy term is called Newtonian mechanics. It's by far the biggest unit in the course, and we'll be spending several months talking about Newtonian mechanics. Over the course of this study, we will investigate curved motion, like a ball on a string and you're spinning it over your head. Planetary motion, we can actually calculate the speeds and the orbital times of planets. Gravitational motion, spiral motion, but these concepts are advanced and we need to be able to walk before we run. So we're going to begin with a very simple type of motion, which is straight line motion. Before we can start to investigate straight line motion, we need to discuss what motion is. So I've got a YouTube video here that I'm going to switch to, and we'll talk a little bit while we're watching the video. So I've moved this video forward a little bit, and what you see is the beginning of a punt return. So there's Devin Hester on his own 35-yard line, getting the ball's in the air. He's going to catch it, and then he's going to return the ball. Now, as you're watching this, you know intuitively that Devin Hester's moving, right? He has motion associated with him. What I want you to think about is how you know, watching the video, that he's moving. We knew he was moving because we were seeing a video that was showing that Devin Hester was changing his location on the football field as time was changing. So we assume that the video is playing in real time, and every second you can see that Devin Hester is moving further and further down the field. And that's all that motion is. Motion, very simply, is a change in location referenced to a change in time. Now the question is, how can we represent this motion so that we can explain it to other people without having to show them a video? Well, there are two ways to show motion. One that's just kind of an introductory idea, which is motion diagram, and then the model that we'll be using in physics, the particle model. So one way that I could show or illustrate this motion to someone who wasn't watching the video is I could take pictures. And in the first picture, Devin Hester would be at the 35-yard line, like we saw. And I could say, okay, I'm going to hold on and not take another picture for another 2 seconds. Maybe after 2 seconds, he's 10 yards down the field. So we'd move our picture of Devin Hester 10 yards down the field. Now in the next 2 seconds, he went a little bit further. So we could have another picture that's spaced out further from the second picture. Then the second picture was spaced from the first. And maybe 2 seconds later, he's in the end zone. But over that period, he's covered more distance than he did in either the first or the second series of pictures. This motion diagram, where we overlay pictures with a defined space of time, is called a motion diagram. And you can see that we're actually getting a little bit of information from this motion diagram. We're seeing that in this case, the person that we're focusing on, Devin Hester, is moving faster or accelerating as time goes by because the pictures are further and further apart. Now, this idea is exactly the idea of particle models, but there's a little bit of problem with what we're looking at here. There's a lot of motion going on as he runs down the field. His arms are moving, his legs are moving, his head is moving, and that can complicate the idea of motion diagram. So what we do is we simplify Devin Hester down to a dot, and we use the same spacing, but we represent basically his center of gravity. Okay, and That's not super important. It's just that we're going to reduce him to one dot. And the second dot would be spaced out the same distance as the second picture, the third dot further than the third picture, and the fourth dot furthest away from all. So in looking at this particle model that we now have, I'm focusing only on the dots, and I see that because they're getting further apart as we move from left to right, that the object in consideration here, Devin Hester, is accelerating. That's it. That's the whole lecture, just the idea of what motion is, distance, and time, and how we can represent it in terms of a model that we can put on paper. Your problem set for this section can be found on page 33, and there's only 4 questions, 1 through 4, and you're required to do all of them. In addition, after you finish the problem set, there's a mini lab associated with this section. You need to, I have toy cars in the classroom, and I want you to come get a toy car from me, and I want you to create 3 particle diagrams next to your homework. And I want those 3 particle diagrams to be labeled and to represent the motion that you observe when you run the toy car on a flat surface, up a ramp, and down a ramp.